Awesome, awesome. So thank you everyone for joining. My name is Jesse Albiston. I'm a partner here at Bitstrapped, a team that works very close with Google Cloud, very close with customers like ThisFish, and we're focused on helping get into the ecosystem of Google and explore the cloud. And we had the pleasure earlier this year and a bit into the previous year collaborating with Eric, the CEO of ThisFish, and Deepak, data scientist from ThisFish, on some really interesting technology. And we worked hard to get folks from Google as well as folks interested in and through the ecosystem of Eric and Deepak's team. So without further ado, I wanted to flip the mic for them to share a bit more about their business, their team, what they're looking to do in the future, and all that's been through it. So without further ado, Eric, I'll throw the mic over to you, and you can start sharing your screen.
How's that? Can everybody see the screen?
Looks great.
Okay, great. Yeah, so thanks everyone for joining. I'm just going to sort of kick off the webinar by giving a brief overview of ThisFish and what we do as a business. Then I'm going to talk a little bit about the use of AI in the seafood industry. Some of you are from the seafood industry and others are from the tech industry. So what I'm going to do is give a bit of an overview of how AI is currently used in the industry, and then I'm going to hand it over to Deepak, our data scientist and R&D engineer here at ThisFish, to give you a more deeper dive into our Tally vision and our use of computer vision. So at ThisFish, our mission is really to help drive profitability and sustainability in the seafood industry, basically through better data, digital, real-time, and accurate. And we do this by providing software and artificial intelligence to the seafood industry. In general, the problems that we're trying to solve really are around the inefficiencies and the cost of manual data collection, lots of paperwork in the seafood industry. And that's really about helping customers reduce their labor costs. The second challenge that we're trying to meet with our technology is improving process and inventory control in the seafood industry. Everybody knows seafood is pretty expensive, and so it's really important from a business perspective to control your raw material costs and have really strong inventory and process control. And then the final thing that we help customers with is really around compliance, improving their traceability, the speed of recalls, the granularity of recalls, and ensuring that there are no data errors or reduced data errors to improve compliance for both food safety and different types of certifications. So the software that we've developed is called Tally, and it really enables companies to automate and digitize their digital work or their workflows in production, quality control, inventory, and traceability. And Tally is really a platform with a variety of different types of technologies plugged into it. It's really a smart manufacturing, smart supply chain platform for the seafood industry. And those type of technologies, of course, include cloud computing, and we're a Google Cloud customer. IoT sensors, artificial intelligence, advanced analytics, and some IoT hardware as well. So we have a suite of products, including our main platform, Tally. Tally BI is our advanced analytics platform that is plugged into our Tally software. Tally Bot is our a little digital droid. I call it like the R2-D2 of seafood processing. We can program it with standard and machine learning algorithms to perform a number of kind of automated tasks in factories. Tally Vision, I won't go too much into that because Deepak is going to talk a little bit about that. And then Tally Tag is a cold chain sensor that we've recently integrated into our platform. So that kind of gives you an idea of the suite of products and services that we provide to the industry. We've also done a lot of work analyzing the use of software and AI in the seafood industry. And so far we've assessed about 365 different software applications that's used across the seafood supply chain. And what we've discovered is about 31% of these softwares are using some form of AI, and about 9% are using some sort of blockchain technology. And Over the last 10 years, there's been a real explosion of the launch of new tech companies in the seafood industry. So this chart here, you can see the growth that really peaked in 2018 and 2019 with about 30 new companies, over 35 new companies being launched in those 2 years. And you can see here the orange represents companies that are deploying AI and the blue is blockchain. So you can see that over the last number of years, there's been a large number of companies deploying AI. And all of this explosion in technology for the seafood industry is really a result of three enabling technologies. One is the launch of cloud services in a 5-year period between 2006 and 2010. That includes, Amazon Web Service, Azure with Microsoft, and of course, Google Cloud. Then, of course, and that basically has put computing everywhere. And then we had the launch of the iPhone and the Android phone, and that put a lot of that cloud computing basically into the palm of our hands. And then we saw also the launch of Bitcoin, which kind of launched a number of distributed ledger or blockchain technologies that we've seen mostly in the traceability space. And a lot of this explosion in technology in the seafood industry is really being driven by a meta trend, and I call it the fish and chips index. And that is, since 1990, the cost of seafood, according to the FAO Fish Price Index, has gone up by about 60%, whereas the cost of semiconductors or computer chips have actually gone down by about 50%. So these are kind of the enabling trends that are the reason why we're starting to see a lot more technology in the industry. Technology is becoming more affordable and accessible. At the same time, seafood continues to get more and more expensive, relatively speaking. Nevertheless, how technology is deployed across the supply chain varies quite a bit from where you are in the supply chain. So what you can see in this chart here is that there are a lot of technologies that are currently being used in fisheries, but most of it is not deploying any type of AI. The AI that is being deployed in fisheries, most of it is around computer vision technology, basically using computer vision and AI to monitor fishing activity at sea and automate the analysis of video. So increasingly, there's more and more fishing vessels in the world that are putting video cameras on board to monitor fishing activity at sea to ensure they're legally fishing and fishing within their quotas and this sort of thing. There's also a lot of AI in the aquaculture industry, and especially computer vision, where they're using computer vision underwater to basically track the growth and the health of fish in farmed pens. So there's lots of AI really in the aquaculture sector, and it's really growing. The area that we mostly work in is in the middle of the supply chain with often seafood manufacturers and seafood distributors. So you can see there's not as much technology being deployed in that sector. And today we're going to learn about how we're actually using AI and computer vision to really help improve the visual inspection in the seafood industry. Because generally speaking, in the seafood industry and in food in general, a lot of the quality inspection is very manual. It's sensory evaluation by a human. And the data is typically recorded on paper. So this image here shows you what is typical in the seafood industry for how quality inspection happens. However, we feel that there's a lot of opportunity for computer vision in food inspection because as I mentioned, there is a lot of visual inspection, from visually inspecting raw material like fish coming into a processing plant, visually inspecting semi-finished products, and then of course inspecting the finished products, not only the quality of the food inside the products, but often just visually inspecting labels to ensure that there's compliance with regard to food labeling. So we've we believe that there's a lot of opportunity for computer vision in the seafood industry. And so what Deepak is going to do is tell you about some of the R&D work that we've done over the last year in developing our new product called TaliVision.
Yeah, thanks, Eric, for that wonderful introduction and overview of ThisFish as a company and the growth of AI within the fishing industry. So TaliVision is our solution for automated continuous inspection. The first iteration for this solution, we built in-house, and we actually deployed it into our client's production facility to actually assess the quality of fillets as they were as they were processing those the raw material from into fillets. So its applications, as we can see, is like which we deployed it for was to measure the size of the fillets, to classify its color, and also kind of like determine the different kinds of defects that were present within the fillet. Okay, to kind of like give an overview of how this solution worked, we have a diagram here that kind of like just walks through what we built. First, we had the camera mounted on a conveyor within our client's facility, which captured videos for the fillets as they pass through the conveyor. After getting that video, we sent that video to Google Cloud to store those videos into buckets. Then we used our compute engine resources to actually extract image frames from those videos. Once we had those image frames, we passed those images into our model detection algorithm in order to kind of like to come up with defects and also to draw bounding boxes within the images. And then once the model detects different kinds of fillets and its defects, we save the images data with bounding boxes into the storage buckets, and also the data itself, we hosted it in our Cloud SQL database. Then after that, our Tally BI dashboard software queries that data for our clients to view in a dashboard for them. So I'll just go over some kind of like defects that we had within our salmon fillets for our clients. And the first one is, as we can see here, is inoculation, which typically occurs for farm fillets. This is kind of like when the salmon fish itself is kind of like in its early stages, they would put a needle through it to kind of like increase or boost its growth. So that's why it would leave these marks within the belly region, as we can see from this image. And another example of defect that we have is gaping. And this usually occurs in terms of like how the fillet, how the fish is handled. It's like, say if someone was carrying it through its tail, using its tail, it would actually stretch the fibers, the muscle fibers for that fillet, for that fish. And we also have trenching, and this is often associated with in terms of the machine which is responsible for removing the pin bone from the fillet. And often the issue with this is that in terms, because it's usually handled by machine, it's kind of like helps kind of like the clients determine in terms of like how to calibrate the machine to avoid having massive trenching, as we can see from these images. The next defect we have is softness. It's just generally considered kind of like mushiness or softness of fillet, which kind of like indicates that the fish wasn't handled correctly or appropriately when it was harvested and brought into the production facility. And now I'm just going to go show you a demo of the Tally BI dashboard that we have actually built for our clients to kind of like see these results and to come to allow them to have insights in their production run. So this is an example of a test run for our client. So within our Tally BI dashboard. So first we allowed them to select a particular date and kind of like what shipment and also job order they want to view. So for the first chart, we just kind of like give them like a high level view of the distribution of regular fillets versus the defective fillets. Regular fillets are just perfect fillets with no issues, while defective fillets has defects, as I showed on the images in the previous slides. So within those defective fillets, we can see that some of them are bruised, softness, and majority of them were trench. And on the next chart, we also have a chart that displays the salmon color distribution, where salmon color scale is just kind of like a standard to assess the quality of a fillet according to its color scale. Different types of species would have a different standard value for this. And for this production run, majority of them were number 24. And and the next chart, we also show kind of like the length of the different defects, as shown here for the gapes. And for trench, as I mentioned when going through the defect for trench, is that this is usually done by machine, and we want to also kind of like give our clients an insight of what the length, what typical length for the trench are, so kind of like they can adjust their machine calibration to reduce this. And we also give them kind of like a chart to display the number of fillets that are processed through time in 30-minute intervals. So for example, from 7:30 to 8, how many regular fillets and defective fillets there are. Next chart, we also give a yield value, which is the ratio of the raw material weight that was that for production divided by the output of the processing. And next, we also give them samples of images, as we can see here, an example of softness, and also an example for trenching on a fillet. And one more example here, it's the gape, as we see from this fillet here. And not just the defects, we also give them samples for the color scale for different fillets that are processed. As we see here an example of a fillet that's color scale 24. So that's our UI for the dashboard. And the next thing I just want to go over is the challenges that we face for our first iteration for this in-house solution. It was high cost, because we were kind of like fully dependent on Google Cloud to use to store our videos, process that, use different kind of compute engine to process those into frames, and it was turning out to be massively expensive for us to pass it to our clients. So it wasn't really scalable. And also the issue was like high latency. Before the fish has passed through the conveyor and before our clients get the results of the detections, it was taking us at most 5 to 10 minutes for that data to be live on the dashboard. And because of high latency, we were not able to integrate with hardwares. Because one of the reasons for hardware integration is that once kind of like the fillet passes through the conveyor and the model detects that it is defective, we want to send that data as a signal to a hardware that would segregate this defective fillet into a separate bin from those regular fillets. And since also due to high latency, we were not able to do live streaming. And when we partnered with Bitstrapped and Google Cloud to come up with our TeleVision 2.0, the objectives were first to lower cost, to get real-time results. Getting real-time results would allow us to then integrate with hardware, and also one kind of like particular use case for hardware integration would be automated sorting of fillets. And finally, we would like our clients to also would be able to live stream the production process from their camera, and also from their from their phones, and as well as their laptops or computers. So working with Bitstrapped, this was the infrastructure that they came up with to solve this issue that we had. So first, again, we still have our conveyor with a camera mounted, but instead of just using a camera that only recorded videos, we have a smart edge device, which has a camera itself and also with the server, with the hardware within it. Now, within the camera, it's actually a smart camera, which allows us now to capture frames and also kind of like do image processing, do defect detection, and also fish size and color estimation. So from the point that the fillet passes through the conveyor, all this process happens within less than a half a millisecond, which was a big win for us. And once we have the images with bounding boxes drawn for the defects and also kind of like detection data, we still store this data into Google Cloud. We store the images with bounding boxes into the storage buckets and the detection data into Cloud SQL, which is then still queried by our TaliBI dashboard to display it to our clients. So this was a high-level overview of the solution that Bitstrapped came up with. But in the next slide, I'll go in more detail in terms of how this works. So we have a camera, which is now a smart camera that does all the processing and also kind of like detections, fish size estimation, and color estimation. And once we have those images with bounding boxes together with the detection results, we send that to Google Cloud. And the way that this data is sent to Google Cloud is through invoking a cloud function with a secure HTTP request. Once the cloud function receives that HTTP request, first it authenticates. After the authentication is done, it actually saves the images to the Google Cloud storage. And then it further validates the data results to see whether if it's in the correct format before adding that into our Cloud SQL database. So that's kind of like how the camera does how the camera stores the data into Google Cloud. But on our client side, we have our Tally application, which is where our clients would input their input information regarding the production run, such as the raw material information, the species, the date for harvesting, and such. And that data is typically stored in an unstructured format. And we also have our inbuilt in-house built solution for extracting, transforming, and loading this data, which turns this unstructured data into relational table structures, so that then, hence, we can save this data into the Cloud SQL database. So what happens here is that the production information from harvesting the fillets, harvesting the fish, we can now link that data to the quality data from inspection, and within the Cloud SQL database, then our Tally BI software queries that and shows that to our clients. In the next slide, I'll just show some videos of like how this solution works. So as fillets are passing through the conveyor, we see that the bounding boxes are being drawn, and they're being classified as fillets. And whenever it sees kind of like there's a defect, it will also highlight that as a defective. Sorry for the bad quality for this, but we can also see that when there's a fillet that's upside down, it also classifies it as well. And this kind of fillet that we see right now, it's a farm fillet, which is typically lighter in color compared to wild salmons, which we're going to see on the next slide. Okay, so let me do this here. And this is a wild salmon, as we can see, which is way darker. Let me just increase this quality here. Way darker than the farm salmon. And as we can see, same as it determines the fillet, draws bounding boxes. And whenever there's a defect, it would also highlight those defects. So one thing that we're able to do now is actually provide traceability for our clients from farm to factory, because it's important for them to kind of like have insight in terms of how kind of like how their suppliers, how the raw material that their suppliers supply to them, and then its quality as well after they have produced it. So for example, now we are able to link, for example, for a shipment, let's say we got it from a certain supplier and the catch date was with a particular catch date, and also together with the species information, what kind of defects, how many defects did we find from that shipment, together with what was the average color for that shipment. And finally, the next steps we have is an automated continuous inspection, and also providing live streaming for our clients.
So that's the end of the presentation on the technology. The one thing that I'll also just add that I think is quite interesting is that, from working with our different customers, what I've sort of realized is that there's not necessarily a standard for quality control, from one company to the other. Even, for instance, the Samofan, which is a color scale that's used widely in the farm salmon industry, it's pretty subjective how humans actually look at a salmon and determine where it actually falls on the color scale. And that's partly because, color is often not that consistent across the fillet. Some people may see things a little bit differently than others. Even on things like whether something's a trench or a gape, sometimes, there's a bit of a gray area. And it's kind of interesting working with our customers and seeing the different types of quality, standards that they put in place. So I think that, one of the advantages with AI and computer vision is that, perhaps in the future, what we can start to see is a more standardized quality control throughout the industry, because we could basically train models from multiple companies, so that there's more of a standardized or university quality inspection across the supply chain. Because the one thing that I hear from a lot of customers is, right now, if a seafood processor sends some fish to a retailer or restaurant, and the restaurant or retailer complains that hasn't met a certain quality standard, right now, there's lots of debate that goes on whether or not the order has met the standard, and that's because the quality inspection is just a random sample. So, maybe 20 or 30 samples have been randomly selected and evaluated in a production lot. And so there's a lot of subjectivity in quality control at this time. And I think that by doing continuous automated inspection, a lot of that subjectivity will be gone, because right now, we could provide basically an image of every single fish fillet that is now being processed in a company. And so if suppliers know that a particular manufacturer has extremely detailed quality controlled data, they'll be less likely perhaps to put a claim in, knowing that the processing plant has a lot of data to back up their quality claims. So that's our presentation, and we'd like to open it up for questions or comments now. And for those of you in the industry, if you'd like to have a demo and talk to us more specifically about some of the issues that you're having in quality control, there's a QR code here that you can scan, or you can go to our website and just type in this.fish/demo, and you can fill out a form and request a demo with the company. And you could either put maybe questions into the chat box, or we can perhaps also turn on the audio, Jess?
Yep, I think folks can unmute and feel free to ask your questions. I have one question as you're going through it, Eric.
Sure.
For examples where like fillets are identified with more than one defect, like softness or trench, is that like is the count established defect specific, or would it prioritize which is the stronger defect in the fish?
I think the way, and Deepak can correct me, I think the way that we did the algorithm is that if it's either or. If fish fillet is defective, it could have 3 or 4 defects, but we just classify it as defective. But then we're also counting individual defects. So, when you see the total number of defects, that's higher than how many defective fillets there are, likely, because as you saw there, a defect could have a bruise and then also a gape or a trench on it as well.
Well, it's great to hear the facts of like how those defects occur and like the Q&A process. Like I think the juxtaposition that I noticed from the start of the presentation, which is like the photo of someone with a handwritten piece of paper doing quality versus what you shared as what you guys have built and as your product is an incredible example of AI. One of the most exciting ones that we've seen used in creating a bunch of ideas of how companies can improve their quality. Is very, very cool. I see a question came in from Nick. Have you done much work with whitefish like cod or pollock fillets?
Yeah, so the first model we did was salmon, so we haven't done any other work on other fish species. But what we can do, and I can talk a little bit about how we would onboard a new customer, a new fish species. And basically what we do is we'd set up the camera on a conveyor belt, take maybe a couple thousand images of those whitefish, and then we would work with the quality control department of our customer and annotate those images. So the one thing about the type of computer vision that we were working on, it's actually humans that initially annotate and draw those boxes around the image, around images, and that becomes a training set. And then we use that training set to basically train the algorithm. So for instance, if we're doing some sort of whitefish inspection, depending on the number of things you want to classify, like, maybe on whitefish, there are 3 different types of defects. What we'd probably do is collect maybe 300 to 500 images for every class of defect, annotate those images and then train the model and then run it in the factory. So, even with the salmon processor, what I've found is, again, the quality inspection seems to be a little bit different from one company to the next. So if we train an algorithm in one factory and then take it over to another factory, that factory might not be particularly happy about how the television's working because it's classifying fillets according to somebody else's standard. So, generally speaking, we're working with the company's quality control departments to ensure that the quality standard is meeting what that company standard is.
Very cool. I see Peter has a hand raised there. You want to give your question, Peter? Oh, you're muted.
I'll put it in the question box, but can this be used on live fish as well?
The camera that we're currently using is not an underwater camera. So if it was in an aquarium, potentially you could use it, looking into an aquarium. But if you wanted to actually put it underwater, we'd have to get a different type of a camera for that type of inspection. And I should mention that there is a lot of computer vision that's currently being used in the aquaculture industry underwater in pretty severe conditions.
Okay, thanks.
Yeah.
There's a question from Jim.
Yeah.
Line speed maximum that television can handle.
Yes.
I'll hand that over to Deepak.
I can answer that one. In terms of the line speed, it's like trying to find a medium in terms of the speed and also kind of like the frame rate your camera is capturing. So kind of like we can adjust the frame rate from the camera itself to adjust to kind of like what the line speed is, but we can't kind of like set a standard because like that's kind of like an experiment that has to be done with the speed of the computer and as well as like the frame rate the camera is capturing.
Mm-hmm.
I wonder if that's a good answer. And Jim, do you have a specific speed that you had in mind or that you see in your line of work? If there's a follow-up question, feel free to type it in the box. But Rodrigo, I'll jump to the next question. How accurate are those models? I'm thinking in key measures like color detection on SAMO fan scale.
Yeah. So I can comment on the color one. I would say that we have some more work to do on the color scale, and the reason for that is, from my understanding, the industry standard and Rodrigo, if please comment on your own thoughts on this. It seems to me the industry standard is generally to take the portion of the back of the salmon fillet and do the color rating based on the back of the salmon, not on the belly flap. So the current model that we've built really takes an averaging of the color, including the belly flap. And what we found is that sometimes in processing, the membrane is left on the belly flap, and the membrane can be quite white, and so it has thrown off the color scale in our early model. So what we need to do is kind of work with the company and design, a more, I guess, accurate or customized model for color rating. So yeah, and the other thing that I'll mention is, early on, for instance, we initially trained the model mostly on sockeye fillets from Alaska. And so the gaping on a wild fish is typically, and I used to be a salmon fisherman, is typically on the tail, right? Because the fishermen are grabbing the fish by the tail and throwing the fish off, and it basically is tearing the tail. So what we found is on the farm salmon fillets, all the gapes that were happening more around the neck were being classified as trenches, because most of the trenching happens at the front of the fillet. So once we realized the bias in the model, what we then did is we took a whole bunch of images with misclassified trenches on farm salmon fillets and reclassified them as gaping and put it back into the model. And I think that's one important thing to understand, is that even if the computer vision model doesn't operate that well initially, you can retrain and improve the model. And generally speaking, because the model's being trained by people, the visual inspection is as good, or if not better, than human inspectors. And that's particularly because, and I've heard this from some customers, over an 8-hour shift, what they can see in the 6th, 7th, and 8th hour that somebody's doing QC inspection, sometimes the quality of the QC inspection can go down because the worker is tired and this sort of thing. Whereas with the computer vision, obviously it doesn't get tired. It consistently will evaluate all the fillets throughout the day.
Awesome. Question from Kevin Edwards. Can the camera detect parasites or measure defect dimensions against specs?
Yeah, so again, the general rule is if you can see it with the human eye, then we can train a model to detect it. So I've also heard this from another customer that, I didn't even know this. Apparently, there's different types of bruising. Sometimes the bruising on wild salmon could be caused by parasites, and there's a bit of a visual difference compared to a bruising from some sort of impact. So we can definitely train a model to see parasites. Also, obviously, if you're putting it on a candle table like a whitefish fillet, you could have a camera over it so that it's automatically looking for the parasites. Maybe after they're doing parasite removal, so you do a final QC, and then it would just flag if it sees any fillet with a parasite in it. So I think again, the easier it is for a human to see, the easier it is for a computer vision model to also see it.
This is great. The big question here. So I'm a student in fisheries. It says coming in from Nguyen. I'm sorry if I'm pronouncing your name incorrectly. Student in the fisheries science and learned computer vision myself. I did some object detection, classification, and segmentation projects. What advice would you give a student like me about looking for a career in fisheries who want to do applied computer vision in fisheries?
Yeah, my advice, and Deepak can chime in here. My advice is maybe to take some courses. There are a lot of good computer vision and AI courses online on programs like Udemy or Udacity or a bunch of online programs. That would be my recommendation.
Yeah, I'll also come over top. There's Coursera. Google Cloud has a ton of learning sessions. There's a lot of new products that have come out in the last 6 months to explore vision use cases, pre-built models you can tune, and it's quite accessible. So that's another thing to check out. That's a lot of fun. So I have a question, Eric. Obviously, we had fun working with you on this. We saw the technology, but curious for folks and like for companies that would want to do a proof of concept, a first start. Obviously, you explained there's a lot of collaboration, identifying images, labeling images, working collaboratively. What would be like a timeline, estimated level of effort to explore this use case to be built out in a new customer's environment?
Yeah, I would say that we could probably get an initial model up and running probably within 4 to 6 weeks. And again, it depends on how sophisticated the model is. One, we need to build some sort of mount for the camera that's customized to that specific facility. So there'd be a couple weeks there to get an engineer in to put a mount in. We then collect the image collection. Probably only takes a day because there's often tens of thousands of fillets going across a conveyor belt, and then again, depending on how many images you need to train, it could be from 5 days to 10 days to annotate the images. So in our experience, I think Deepak, it took you maybe you could do 150 images or 200 images a day in annotations. So if we need 1,000 images annotated and you have one person doing it, it would take 5 to 10 days to annotate it. And then actually deploying the model onto a camera and stuff, that would just take a day of going into the facility, setting up the camera, deploying the models, and getting it operational. So most of the time really is engineering a mount to mount the camera, and that fits within your production facility. And then second is annotating the images. That the human annotation images can take, as I said, from a week to maybe 2 weeks, depending on how many people are doing it.
Yeah, I think just one thing to add, it's for the engineering, as Eric mentioned, the mount is really important together with a canopy to kind of just avoid any kind of other lights that would hit the fillet that would cause glare and other kind of distortion to the color. Yeah,
like Deepak, so it sounds like you need an environment that's consistently the same lighting. It's really making sure it's the right location, the right environment.
Yeah, and I should mention that as well. The mount also that we developed, what we did is we put a canopy, just a piece of steel on the top to cut down the direct light, because when there's direct light hitting the salmon fillets, it was causing a glare, and that glare obviously basically kills any information that's on that spot. So, but what we wanted to do is build a system that is pretty lightweight and that can be set up and implemented fairly quickly. So we didn't want to construct a very large light box or control all the lighting. What we wanted to do is just cut back the direct lighting and then use the ambient lighting in the factory. And we can calibrate, for instance, the SAMO fan according to what your ambient light is. So, if it's slightly warmer light or cooler light, that really doesn't matter because we can calibrate the computer vision model based on the lighting in your factory.
Very cool. A question from Kevin Edwards, another one. How do you reconcile the fresh versus frozen product for grading glaze on two sides? Is there a demand for that?
Could you maybe explain a little bit more in detail the grading glaze? Are you asking whether we could use computer vision to assess how much glaze was maybe on the fillet? Yeah,
that's a good response. So the first part is the challenge of looking at the dimension of the glaze, and the second is the fact that it seems to be one-dimensional. And then how do you measure whether the opposite side is effectively glazed?
I see. Yeah, I mean, it can be. I've had that question actually come up, whether you could put a camera on both above and below the conveyor belt. Of course, the challenge there would be having some sort of translucent conveyor belt, or at some point in the production, the fish might be slid across some plexiglass, on a slope. So there is a possibility of doing that on both sides, basically. The other thing I should mention is there are more advanced computer vision models out there. I recently saw one that was demoed to me, where you'd have the camera, and by just slightly moving the camera can basically assess 3 dimensions. So it's not using LiDAR or any kind of special technology. It's just using the image, and then it can actually construct a 3D model using the camera. So that I believe there's a company in the United States that has a patent on that technology, but there is some technology on the market now. I would say it's more cutting edge, where you can use computer vision to basically construct a 3D model. So maybe if you wanted to see the thickness of the glaze, you may have a camera that is slightly rotating and then can take a 3-dimensional picture basically of a fish fillet. And I should mention, right now, some of the computer vision models that I've seen that try to take an image and estimate the weight of a fish, I think that they're maybe 88, 90% accurate. However, if you were able to have a 3D image of a fish, so basically move the camera around the fish and get a 3D image, what you might be able to do is get the weight accuracy up much higher, maybe up to 95 or 99%.
Go for it, Diana.
Yeah, this is so great. I was curious, you were mentioning the consistency when it comes to QC, being able, people just fatigue being a problem and being more consistent, which is also a problem we've seen in like early cancer detection in pathology, for example. Pathology is oftentimes affected by the same problem. But my question is are you measuring the impact to like that operational efficiency? Have you figured out what the revenue increase might be by implementing a system like this? Yeah,
I think that we're still, I think, in the early days at looking at the total ROI. I think there are a couple places where there could be ROI for companies. One is if we can do automated grading. So essentially, you don't need workers, on the factory floor. You can basically use television along with an automated piece of machinery that might put out an arm on the conveyor belt and then move a fillet off the belt if it's defective. So, that could significantly reduce labor costs, obviously. The other thing is by having exceptionally detailed QC data, what you might find is the number of claims coming from your customer may go down because the customers know that you have an incredible amount of data to show that you've met spec. And then the third thing that I've talked to some companies about is, especially, over the last couple of years, the quality of the sockeye salmon coming out of Alaska has been, quite varied, and there have been a lot of quality problems. So if they can use this to automatically classify the quality of the product and put them into different product streams. If you have a very high-end premium product, you don't want to be using fish of low quality. And often it's very hard for companies to manually assess a significant amount of the fish to determine what product that should be made out of. So again, if you have a lot better quality data, if today you have a certain lot and you run in the factory and you get extremely detailed data on the quality of that lot, you might know that tomorrow you should not maybe use that for a premium product. You should use it for a B grade product because television showed you that there's a lot of quality issues with that lot.
Super exciting. A couple more questions came in. I'll just quickly cover those ones. So one of the ones here is, if I were to summarize, it sounds like, what is your comment about the future of developing a computer vision application? So like mobile apps on devices versus fixed cameras. Is that something that's been discussed, or is it's really important probably to have that consistency of a fixed setup?
Yeah, I think that there obviously is a lot of computer vision on your phone. I have an iPhone. I have, facial recognition, right? So there's definitely a lot of opportunity to push a lot of this computer vision onto phones for sure. Because the phones are also very powerful computer processors, so you can process a lot of the data there for sure.
I think the idea of like tiering of quality, like Diana, you asked about operational efficiency. Eric, you commented on like different grades of fish. I imagine like the innovative facilities that would look to this use case and technology beyond quality assurance, it comes into being like new product segments. There's obviously buyers who want to pay more for higher quality fish. So there's lots of potential use cases where this technology is going to lead to companies innovating beyond just the Q&A process based on the technology you guys have built.
Yeah, for sure.
I know we've only got 5 minutes left. We're coming to the end here. There's one question from Olav. What is your experience using computer vision in quality grading for whole fish before filleting to identify the best utilization of the actual fish? It's an interesting question.
Yeah, again, we our current model right now is just on fish fillets. But if there is any kind of identification that you can do, like a human can see a certain quality issue on a fish, we could train a model on whole fish based on size or shape or other kind of defects on the exterior of the fish. I know that I think in Alaska, I've talked to some companies that they can determine the quality of the fish basically on the color of the skin of the salmon, I guess, depending on where it's caught. If it's more upriver, have lower fat content than at sea. So you could put a quality grading in based on is that caught out at sea or more in river where the quality of the fish has gone down, and you can see it externally on the fish itself.
I remember probably about 10 years ago, I was in Japan at the fish market, and they had all the big tunas, and they had just the tail sliced off and the very end cap of the flesh exposed. It seemed like that's how a lot of the buyers were making decisions. So it's interesting, interesting angle as well.
We have another project that we're also working on, looking at cutting the tuna and looking at the salt in the tuna. So a lot of the canned tuna that you buy in the store, it's actually being brine frozen at sea. So the fish go into a big slush of salt, basically 25% salt solution. And if the fish doesn't freeze very quickly, it'll actually start absorbing the salt, and you can kind of see a salt ring on the inside of the tuna. So we've been doing some work with that, and that's a project that we're continuing. And there's lots of interest in the industry because salt quality is a big problem in the tuna industry. Often, if the fish has high salinity, a lot of companies don't want to buy it. Consumers obviously are, sensitive to high salt in their food.
Wow. Well, I think we should end there. We're at our full minute to go. So with closing notes, thank you, Eric. Thank you, Deepak, for walking through the demo, answering lots of questions. That was a really engaging Q&A session, really exciting. So the session was recorded. So anyone who was here and those who were not will also receive that. Oh, we have one final question. If that wasn't a mistake, feel free to ask it. But otherwise, thank you guys for joining, and we will send the email out shortly. Thank you all.
Great. Thank you. Take care.